Alright, so today we're going to look at our unit conversions. So going from, for example, moles per litre, which is our molar concentration, to grams per litre, which is our mass concentration, and going back. And then we might also look at going from grams per litre to milligrams per litre and back, and then to micrograms per litre and back. Just to mention something, milligrams per litre is also written as parts per million, and micrograms per litre is written as parts per billion. Now, people get a bit weirded out by this, but it's really a lot simpler than it seems. So here, for this first one, a way to think of it, instead of thinking of concentration, let's just think of, if we've got a value of moles, if we've got a value for N, and we want to convert that to a mass, what do we normally do? We look at our triangles, for example, and we go, you know what, I've got N, I want to go to mass. Mass equals N times by M. So what have we done? We've just multiplied it by the molar mass. All right, now looking back up here, we're starting with moles per litre, we're going from grams per litre. All that's changing is moles is changing to grams. So that means that moles is going to a mass. So how do we convert between moles to mass? We simply times that by the molar mass. We don't need to stress about the fact that it's per litre, because it doesn't change anything. The per litre is not changing. The only thing that's changing is moles is changing to grams. And we know that to change moles to grams, all we need to do is times by molar mass. Likewise, if we've got a mass, we've got a mass in grams, and we want to make that a mole, if you're given, 45 grams of something, how many moles? We know that from that triangle over here, we're just going to get the mass and divide that by the molar mass. I might just write mass there and molar mass just to make sure. And that'll equal the moles. So likewise, going back here in this direction, here we're just going from grams per litre to moles per litre. The litres isn't changing, per litre stays the same, so nothing changes there. The only thing we need to change is the grams back to the moles, and therefore we just divide by molar mass, as we know from that sort of thing. So back up here, state the mass concentration of a 0.015 mole per litre solution of sodium carbonate. So what's a mass concentration? Something in grams per litre. So we want to go from moles per litre to grams per litre. And again, we know that from what we've just done, we're going to multiply that by molar mass, but all we really need to think about is we're just changing this bit here, moles to grams. Litres, it's not changing. It stays constant on both sides of the conversion. So our mole concentration is 0.015 moles per litre. We're going to multiply that by the molar mass. I've worked out the molar mass earlier just to not have to waste time finding it because we know how to do it. So we're going to have 0.015 mole per litre. I'm going to write all the units in just so you can see why it cancels out. Times by 84.007 grams per mole is our units for molar mass. Plugging that into a calculator gives us 1.26 grams per litre. Where do those units come from? If we look at these bits here, we've got, might use a different colour, might use red. We've got moles per litre multiplied by grams per mole. These are going to cancel out, and that's going to give us with grams per litre. Beautiful. Just going to get rid of that and get it out of the way. So likewise, for this question up here, state the molar concentration of a 0.5 grams per litre iron sulfate solution. So we're told that we have 0.5 grams per litre. Now, if we're going from grams to moles, we know that N is equal to mass divided by molar mass. Therefore, we're always going to divide our mass by our molar mass to get moles, which implies if we're going from mass here to moles here, again, we're just going to get our grams, divide it by molar mass, and that's going to leave us with the moles. So therefore, all we have to do, we know our molar mass here is this number, and it's just something that I looked up earlier. 0.5 grams divided by per litre divided by 151.908 grams per mole. And that's equal to 0.5 times 151.908 into a calculator, gives us 75.954 moles per litre. Beautiful. I'll do these next ones as well. State the concentration in parts per billion of 2.5 milligrams per litre of Hg2+. So if we've got 2.5 milligrams per litre and parts per million is in micrograms per litre, there's 1,000 micrograms in a milligram. Again, the per litre bit, it's not changing, so we don't have to stress about it. All that's changing here is the micrograms is going to, sorry, the milligrams, I meant to say, is going to micrograms. If you've got 1,000 micrograms in 1 milligram, then for every 1 milligram, you've got 1,000 micrograms, so we're going to multiply this by 1,000 to get there. That implies that we have 2.5 milligrams per litre times by 1,000 is going to equal 2,500 micrograms per litre. And then for this last one up here, state the molar concentration of a 25 parts per million solution of lead oxide. So we've got 25 ppm. Parts per million is equal to 25 milligrams per litre. First step, let's convert that to grams per litre. So if there's 1,000 milligrams in a gram, that means we're going to divide this number by 1,000, which means that we'll get 0.025 grams per litre. Now, if we've got grams and we want to convert that to moles, what do? Moles is equal to mass divided by molar mass. So we are going to divide this number by molar mass, and that will turn that grams per litre into mole per litre. Just going to quickly double check the molar mass of lead oxide, which you know from looking at your periodic table, it's just the molar mass of lead plus the molar mass of oxygen. That number is 223.2 grams per mole. Therefore, 0.025 grams per litre times by, sorry, that should be divided by 223.2 grams per mole gives us an answer of 1.025 1.12 times by 10 to the power of minus 4 moles per litre. Now that's a really small number, but that makes sense because you've only got 25 parts of a 1 million part solution. So it makes sense that this number here is really small.